Good morning, everybody. My name's Scott Power. I'm the Director of the Centre for Applied Climate Sciences at the University of Southern Queensland. And for those of you who don't know, we have a staff of around about 20 people scattered across southeast Queensland, Melbourne and United Kingdom. And we conduct research, extension, product development, monitoring and evaluation and adoption to help people manage some of the risks they face from both climate change and climate variability. And we help them seize any opportunities that may arise. And we also employ a network of climate mates right across Northern Australia who act as champions in the use of both meteorological and climate science in decision making. And finally, we have around about 15 PhD students, both here in Australia and also in Southeast Asia. And it's my, before I introduce the speakers, I'd like to acknowledge the traditional owners on the land on which we gather. And we'd also like to pay our respects to elders past, present, and emerging. And it's my great pleasure this morning to introduce our two speakers. And our first speaker will be Tanya Fielder, Dr. Tanya Fielder, who's at the University of Sydney. And Tanya is a lecturer in the discipline of accounting, and she's very interested in the integration of physical climate science, or physical sciences, I should say, into work practices, business strategies, and disclosures. And Andy is a professor in climate science at UNSW, and he's also the director of the ARC Centre of Excellence for Climate Extremes. And he has multiple senior advisory roles in climate science for both the federal and New South Wales governments, as well as senior national roles in e-research infrastructure. And if you didn't know, he's also a recipient of an Order of Australia medal. So I'll hand over to you now. Thanks, guys. And they're going to be talking about business risk and the emergence of climate analytics. Thanks, Tanya.
Okay, well, first of all, thank you very much, Scott, for the invitation to discuss our paper today. We're really looking forward to the discussion that will follow. As Scott mentioned, we're going to be discussing business risk and the emergence of climate analytics. And this was a paper that we published, that was published earlier this year in the journal Nature Climate Change. So Andy, if you can go to the next slide, please.
That's interesting. Why does that happen? I've never seen that happen before. Sorry, fault, technical glitch.
That's all right. There we go. Okay. So in terms of what we're going to discuss today, first of all, we're going to look at, I'd like to discuss some of the opportunities for research impact and engagement in this space. So just discussing some of the special issues and opportunities that exist in business journals in particular, and some of the experiences that Andy and I have had subsequent to the publication. Then we'll discuss what our paper is about and why we had to write it. Then Andy will take us through climate models, what they do and they don't do well, and then we'll look briefly at what this means for corporate entities from a disclosure and accounting perspective, as well as what it means for central banks, and then where to next. And apologies in advance, a house is being demolished about 10 metres from where I'm talking to you at the moment, so hopefully it's not too loud. Okay, next slide, Andy. All right, so in terms of opportunities for research engagement, this area I think is really ripe for opportunities in terms of interdisciplinary research, mixed methods, also funding opportunities. So there are quite a lot of opportunities that exist internationally. There is, for example, the INSPIRE program, which has been established in consultation with what's called the Network for Greening the Financial System. Now, the Network for Greening the Financial System is a network of central banks and supervisory authorities. So people such as the Reserve Bank of Australia, but also the Bank of England. I think the Federal Reserve is now a member. APRA, so the Australian Prudential Regulation Authority. So they're very interested in understanding how climate change will affect the global financial stability. And so they've set up this research program. So there's funding there as well. A number of the FT50 journals, so FT50 stands for the Financial Times Top 50 journals, so the journals that Financial Times journalists go to conduct their research and also to source academics to comment on media articles that they might be writing. So a number of those journals, for example, Management Science here on the right, have recently had special issues or will have special issues coming up in the area of climate change. One of the challenges is there's still a reluctance in a lot of these journals to look at interdisciplinary methods. But I think it's worth rattling the cage. So anyway, there are obviously journals such as Nature Climate Change as well, which are really interdisciplinary in their approach. Now, since we published this paper, we've also had quite a lot of engagement with a variety of different types of business organisations. For example, Standard & Poor's, the credit rating agency, UBS, the International Investment Bank, the NGFS that I mentioned before, so the network of central bankers. So there's also a lot of opportunity to be able to demonstrate impact, which we increasingly know from a research and also from a grant perspective is important to be able to demonstrate. Okay, so we'll go on to the next slide, Andy, if that's all right. So the paper that we're talking about today is this one here, Business Risk and the Emergence of Climate Analytics. And in terms of the authors on this paper, it was a really fun paper to write because of the mix. So we had 3 climate scientists on the paper, myself, an accounting academic, but also we had 2 consultants on the paper, one being a former FT journalist. So we had also a real sort of business perspective, which helped to inform the paper. Okay, so next slide, Andy. So the reason we wanted to write this paper was because of the recommendations that were published by TCFD in 2017. So for those of you that are not across TCFD, this stands for the Task Force on Climate-Related Financial Disclosures. Now, this was a task force that was set up by the G20 finance ministers following the financial crisis in 2008, 2009. And so basically first they set up what was called the Financial Stability Board, and the role of the Financial Stability Board was to uncover any sort of emerging risks that could threaten global financial stability. And one of the risks they identified was climate change. So from this, they set up a task force on climate-related financial disclosures with the idea of bringing climate-related information into the mainstream annual financial filings of firms, so basically into their annual reports. And this was a really, really significant move. Now, as a consequence of that, there's been an explosion of physical climate risk scenarios and analyses and disclosures made in the market, predominantly outside of financial reports, so in sustainability reports or in standalone TCFD reports. But the problem with this is, well, I suppose historically there's a problem with greenwashing. Yeah, so around any form of sustainability disclosure, we know that this is a problem. But the difference here is when firms are disclosing climate risk, that goes into the market and it informs how investors behave, what they invest in, then there is a potential for significant capital flows to be redirected away from areas, away from companies, even entire jurisdictions, countries, etc. So if you think, for example, about credit rating agencies and how they rate sovereign bonds, so there's a potential for capital to be directed and misdirected if those physical risk scenarios are not done well. So we wanted to address this so that we could encourage businesses to give the types of information that is actually relevant, rather than, you know, is I suppose even a misrepresentation of what the climate science is telling us. So in all of that, we wanted to provide an objective resource and a warning of the potential misuse of climate models and outputs, and some of the unintended consequences of that. And I suppose also a call to arms for those who are working in this space. So next point, Andy. So in terms of the key points raised in the paper, these were that many projections are freely available, but that this information is deeply complex, particularly for those that come outside of the climate science domain. And so what we did was provide an analysis intended more for a business audience of how climate models can be legitimately or not so legitimately used at different scales of analysis. So from the global scale down to the physical, of a physical asset down to, from the global scale down to the scale of a single physical asset, also in different time scales, and also articulating that climate extremes really matter for the analysis of financial risk. So I think at this point, hand it over to you, Andy.
Thanks, Tanya. I'm just going to say a few more words about some of the key points on this slide from a physical climate risk perspective. That first bullet point about many projections are freely available is, of course, perfectly true. There's CMIP 5 and CMIP 6. There are petabytes of freely available climate model projections available. And to give some of you a sense of how that can be misused, some of those data are saved to 32 significant figures. There are people out there who perceive that to be a measure of the accuracy of the models, as distinct from the precision of the models. The models must be right because they give information on how temperature will change or rainfall will change to extraordinary levels of precision. And of course, in the climate community, we know that that is really just a result of how we solve the equations. We don't think of the models as being that precise, but our customers, if you like, do sometimes misunderstand what our models will tell us. The other thing is different areas of physical risk utilize information at different scales. So that bullet point down from global scale to physical asset, I'll talk about it a little later, but there are people who use the global mean temperature as a metric for how risk will change at a local scale. There's also the fundamental concept in our field of the difference between projection and prediction. We know we cannot predict climate for 2050. We can project climate for 2050, and prediction and projection mean quite different things. But that nuance is totally lost in most circumstances when we translate what we do to people who use our information. And finally, if you go to the literature and you hunt down how climate extremes are going to change in the future, virtually everything you will find talks about climate extremes on timescales of a year. So variables like TXX, RX1, or maybe decadal scale. They don't talk about the changes in quantities that have significant risk to, for instance, a business entity. And if, I've said before, if your business goes out of business because the hottest day of the year increases by 0.2 degrees, your business was probably going to go out of business anyway. It is the rare events, the once every 20, once every 30-year events that really trigger risk within a system in most circumstances. And those things are things that climate models struggle with. So climate models. I'm never quite sure of the background of the audience, so apologies for those of you for whom this is a little bit basic. But it's quite important, and when I talk to people working in economics, they really struggle to always get their head around this. Economic modeling doesn't have the luxury that climate model has, which are the laws of physics. Our models are built around Newton's laws and conservation of energy, conservation of momentum, conservation of mass, which we're pretty confident the laws around conservation of energy are not going to change as climate changes. Those laws will stay immutable. So we have a huge advantage in predicting and projecting climate that the laws of physics should apply for the foreseeable future. Climate models are also eye-wateringly complex. The Australian community climate model access is at the moment about 2 million lines of computer code. So they aren't things that you run on your laptop. Not the last Intergovernmental Panel on Climate Change, but AR5 described climate models as robust at continental scales and above. I want you just to a moment reflect on that comment, robust at continental scales and above, not robust at the scale of your paddock or your property. And finally, and this is really a message to other audiences we speak to, it's important to understand that climate models are not regression or statistically based, they're physically based. Typically, when you use a climate model for a projection, you run it from about 1850, where you've equilibrated it through to 2100. Each pixel is of order 200 by 200 kilometers. Some of them are higher resolution than that now. Some of the AR6 models are run at more like 50 kilometers. So we are moving appreciably to finer spatial scales, but you shouldn't ever use data from a single grid point. You should always aggregate up to 4 or 6 grid points. So the effective resolution of our climate models when we're simulating climate isn't the spatial detail of an individual pixel. Next, climate models struggle with persistence, and they struggle with the simulation of rare events. So an event that occurs once a year, climate models, particularly in temperature, are doing an increasingly good job. But if you look at the skill of climate models in simulating a 1 in 30-year rainfall event, you would be nervous in trusting the detail around those predictions. And most critically, they don't simulate weather scales. So if you think extreme events are the result of a changing nature of our weather imposed on a changing climate, and you think the extreme events that matter to business risk emerge from weather scale interactions, it's important to know that climate models don't represent those things with fidelity. In order to do predictions and projections into the future, we use either representative concentration pathways or more recently the SSPs. Doesn't matter very much. If you've read the latest IPCC report, you know that they use SSPs, but there is a basic translation from RCPs to SSPs. People throw away acronyms like RCP 8.5, where you see global warming of 3 to 5 degrees, which is unambiguously catastrophic and probably not adaptable to. But many global entities require companies now to be stress testing to global mean temperatures of 4 degrees. And quite often, the economic models that do stress testing to 4 degrees don't find a great sensitivity, which I think you could translate as not representing the physical system particularly well. All the way down to net zero emissions at some point with RCP 2.6, where you see global warming of 1.5 or so degrees, which may be adaptable to in sensible ways. These are SSPs or RCPs are not the responsibility or fault of climate scientists. So please don't try and give me a hard time over the design of RCP6, for example. These RCPs and SSPs come from people who focus on demography, technological transfer and innovation, economics and so forth. But perhaps the two most important things is, for the purposes of climate projection, RCPs and SSPs are to first cut interchangeable. And secondly, whilst I hope we aren't so stupid as a species to continue on this pathway, we're currently tracking towards the upper range of those emission pathways. So the latest numbers I have, we're currently emitting about 40 gigatons, 40 billion tons of CO2 annually, which is not consistent with keeping the Paris Agreement. One translates those emissions into concentrations in most of the physical climate models. There are some models now that take emissions directly and utilize those, but most climate modeling imposes a concentration. Most of the time, we simulate the upper, lower, and middle bounds because our climate models might take 6 months to do a set of simulations. They are computationally extremely expensive, and the amount of data they produce stretches our capacity to manage data. So we can't run all of the thousands of RCPs that you see here on the left-hand side. If you look at all the narrow lines, for example, under RCP 8.5, there's 100 or 200 lines there. We only simulate, if you like, one of those RCP 8.5 lines and one of the RCP 6 and one of the RCP 4.5 because it's too computationally expensive to run all of them. Just for information, RCP 4.5, which is the so-called middle scenario, doesn't reduce concentrations in the atmosphere. The atmosphere doesn't actually respond or doesn't really care about emissions. It cares about concentrations. Global warming cares about the concentrations of the greenhouse gases in the atmosphere. And RCP 4.5 doesn't reduce the emissions. They continue, doesn't reduce the concentrations. They continue to increase. Secondly, some of you, if you have ever worked with business, they might ask you to explore the differences between emission scenarios in 2040. Climate models really can't differentiate between the different emission scenarios around 2040 because the concentrations haven't diverged sufficiently in the atmosphere to differentiate between those emission scenarios. So when, for example, an authority instructs business to take account of the differences between 2030 and 2040, this translates really in a climate sense to them not understanding the process by which the climate models do projections, because we cannot tell the difference between the different levels of concentration in 2040 as it relates to climate risk, because it's not long enough into the future. Here's one of the things I tend to show to give people a sense of why we wrote that original paper in Nature Climate Change. The ability to create large numbers of concentrations on the far left-hand side, the various RCPs or SSPs, is well established. We can produce thousands of scenarios around the different emission scenarios. And we can take some of those into our global models and simulate how the climate responds to the different emission scenarios and the different concentrations in the atmosphere. And that's what you see in the middle here. This is from AR5, so it's a few years out of date now, but you can see the climate models clearly differentiate between RCP 8.5 and RCP 2.6 in that middle plot. In other words, very high emissions leads to a profoundly different climate to very low emissions by the end of the century. You'll note that the lobster color line has a lot of uncertainty around it, probably plus or minus a degree or so. And the low emission scenario has uncertainty around it, plus or minus a degree or so, less than that. But there is a clear differentiation. By the end of the century, the high emissions leads to much more warming than low emissions. But note that that doesn't differentiate until about 2060. The lines don't separate. The uncertainty doesn't separate. And at 2030, they are really pretty much the same. So we can say a lot about how climate will evolve in the long term, but it's hard for us to give a accurate or useful prediction of how things will develop over the next 10 or 20 or 30 years. And I have said again that I don't know global mean temperature is what really matters. And so on the far right-hand side, we have the relationship between global mean temperature on the x-axis and the change in the return period measured in years of an extremely wet period co-occurring with an extremely windy period. And this is in terms of days. So what I've done here is mapped how much the global mean temperature changes with how a compound event at a scale of, let's say, Brisbane would change at the extreme of wet and windy. And what you see there is no correlation. There is actually an NAN associated with the R-squared value. What I mean by that is there is no calculatable R-squared value for how those two things correlate. And the reason this is important is some major groups assume you can map in some way from global mean temperature to local climate risk. Here's another example, again, from concentrations, and this time to return periods on temperature. This happens to be for Beijing. And here we've calculated the 20, 50, and 100-year return periods for temperature. So let's think of those as really extreme temperatures. The amount that a maximum temperature will change by for a 20, 50, and 100-year probability. And in that right-hand side, the blues are for the very low emissions and the red are for the very high emission scenarios. And we happen to have CMIP5 and CMIP6 on there for those of you interested. And what I want you to see here is that as you move from left to right on the 20-year or the 50-year or the 100-year, you see an increase. So the return value becomes higher as you increase emissions, as you would expect. More CO2 leads to higher temperatures. But the uncertainty shown by the whiskers is enormous. In other words, there are many climate models that simulate a larger increase in these extreme temperatures under a very low emissions future than other climate models simulate under a very high emissions future. The short story in all of this, at least from my perspective, is using global models to simulate what's going to happen locally is courageous. One of the things that I often hear is it's not a problem that the global models lack this fidelity because we can downscale. We can statistically downscale, and that's absolutely true. You can statistically downscale global models based upon relationships between large-scale observations and what the climate model predicts. And many people do statistical downscaling, and it can be very useful. The problems with downscaling statistically is you assume no reorganization of weather patterns in a changing climate, because if you reorganize the weather patterns, you change the statistical relationship between the previous observations and the climate model. You're broadly assuming stationarity. Regression approaches really struggle with very rare events. And remember, it's the very rare events that probably drive a lot of the risk. And so statistical downscaling, whilst useful, is probably not a solution to the problems we're noting here. And just before anyone thinks I'm a deep fan of dynamical downscaling, dynamical downscaling uses similar physics to our global models. They can indeed run at much higher resolution and probably add value in mountainous regions. But where the global model doesn't get the large scale state right, you end up with translating that large scale global or large scale regional biases into the downscale model. There's no evidence at all that regional downscaling resolves systematic errors in the global model. They work beautifully when driven by era or other reanalyses, but they carry the errors in things like the location of the storm tracks, or simulated sea surface temperatures, or the biases in the overall temperature and rainfall patterns. They carry those biases into the downscaling. And so I think downscaling, both statistical and dynamical, is really useful, but it doesn't overcome the fact that it's extremely difficult for us to say a lot about how climate will change at an entity level. So I drew these up, and please, I'm not going to attempt to defend the precise positioning of all of the elements of these curves. And this is really for a business audience, but I was trying to communicate where climate models have value in assessing climate risk. So on the left-hand side, we have something about the spatial footprint. And if what you want to understand is global scale climate change, I've no doubts that global climate models are hugely valuable to you. And if you want to understand your continental scale climate changes, I've no doubt that global climate models are really valuable to you. But I suspect that once you get down to the scale of a city, there is no useful information content in climate models. And that's a really provocative statement that I'm happy to defend later. I do mean no useful content. I mean, actually, they don't even necessarily, for many variables, tell you the sign of the change. And the same applies in a more complex way and harder to rationalize, really, on the time scale of the event. Global models struggle with various timescales, and you do need to have a deep understanding of the individual climate model or models you're using to understand where those models might have skill, and I suspect they do have skill at some timescales, but I doubt very much that they have skill in predicting the sorts of extreme events co-located with particular regions that we would hope they would have. And I think that's back to you, Tanya.
Great, thanks, Andy. So what does this all mean for corporate entities? So corporate entities are companies that are trying to disclose to the market and assess also internally for themselves the risks they face in terms of damage to physical assets that they own. So, you know, a piece of port infrastructure, for example. Also the operations that they manage. So in terms of demonstrating in cash flow projections, for example, the ways in which those operations might be affected at some future point in time, but also from a supply chain perspective. So even if those damages do not directly relate to the entity and its physical assets itself, the damages might affect the supply chain. So we have corporates globally and within Australia, within the ASX, who are busily trying to understand climate information and its relevance to their assets, operations and supply chains. Now, when we, and as with Andy, I apologise if I'm, I don't know exactly who's in the audience here, so apologies if I'm saying things that are evident to all. But when we talk from an accounting disclosure perspective, there are certain things, qualitative characteristics in information that are important, because these are the types of information that mean, when disclosed to the market, that the people who use that information, namely investors, can actually form a view. They can make a judgment on the risk to a particular corporate entity. Now, the TCFD, when they published their recommendations, they provided some principles for effective disclosures. And these principles are along the lines of some of these qualitative characteristics that are typically expected for any form of financial disclosure. So things such as disclosures should be specific. So again, if we think about an individual physical asset, that is a problem. They should be comparable. So if we think that we cannot use global climate models in a way that enables comparable analysis across different regions for different entities over different timeframes, then again we have a problem. And they should be reliable and verifiable. Now, typically we have financial auditors going through company accounts, going through the data sources that are used by companies in order to publish information. And so there becomes a question there as to how they can verify information that is so complex and really so outside of their realm of expertise. So we have multiple problems here from a corporate strategy, risk assessment and disclosure perspective. Andy, I think the next slide is yours.
I was just going to show this to give you a sense of what's actually happening internationally. This is a slide from the Network for Greening of the Financial System. And this organization has probably trillions of dollars under its influence. When it does its risk assessment, and the risk is to be applied down to quite granular levels, it does some very sophisticated integrated assessment modeling to link emissions with concentrations. And then it uses some very simple integrated assessment modeling to give you a global mean temperature response to those different emissions pathways. Nothing wrong with that. That's been done for many years. And then they do something called temperature alignment, which links how the global mean temperature will lead to changes in physical risk at the granular level. And I think that's amazing to be able to do that. And I think I showed you a picture earlier to show there is no correlation between global mean temperature and local scale physical risk. So this wouldn't matter if this was an academic paper, but this is being used to influence the flow of capital globally. And it risks driving the flow of capital in ways that we don't need to adapt to, instead of areas we do need to adapt to. So it's not an academic risk here. This is actually likely to lead to outcomes which don't reduce vulnerability to climate change, because I think there is a huge leap between how the groups like NGFS simulate global mean temperature and how they then link that to physical climate risk. So how do you move forward on this? First of all, I want to just I've been working in climate modeling since 1985. I'm not against global climate modeling. I think it's a phenomenal facility, a phenomenal technique for simulating future climate. I just worry that it's being misused. Global climate models were built for scientific inquiry, not to tell businesses at the scale of a suburb in a city what their risks would be to climate change. So I think there's a gap between what we built our models for and how some groups are now using them. So what you do if you're a business, well, the first thing I've always recommended is a forensic examination of your accounts. For example, can you see an El Nino La Nina cycle in your sales or whatever? If you cannot see any hint of a variation in your business associated with things like modes of variability, that doesn't mean you're invulnerable to climate change, but it means you probably have a bit of time. But if you can see quite a signal associated with El Nino La Nina cycles, you probably do need to rapidly assess your vulnerabilities, both operationally and in terms of supply chain, and then go to the use of climate science to assess your future risk and your future interdependencies. I think that would be partly based on physical climate risk projections and physical climate predictions, because the IPCC now provide decadal scale predictions and longer time scale projections. But I want to really strongly advocate for expert judgment here, bringing in meteorologists from the area that the business operates in to work up a sense of what vulnerabilities are plausible and what are not plausible, based partly on storylines and scenarios, if you like, to undertake a bespoke analysis based upon multiple lines of evidence. And I emphasize multiple lines of evidence here. So, questions like, what is your exposure to climate risk? Maybe if you can identify those climate risks that you're particularly vulnerable, you can go and talk to climate scientists about the probability of those risks. Where we can't provide those risks, maybe we can develop or co-develop pathways and strategies to provide a robust risk estimate, needing quite a deep collaboration between climate modelers, climate scientists, and I differentiate between the two there, to try to provide bespoke estimates of risk to individual businesses. And I absolutely agree, this is much, much harder than taking CMIP6 models and processing them, but I think it will lead to a much better outcome. And lastly, the ultimate goal here is we need to provide our global climate models as one of the tools for assessing climate risk at a far more granular level. The Australian model runs at about 100 by 100 kilometers, and that ain't good enough. And there is hope here. This is a simulation from the Max Planck Institute in Germany with their ICON model. This is quite an impressive model that can now do global 5-kilometer resolution simulations. At the moment, this would take about 100 years to do 100 years of simulation on Australia's national supercomputer, which gives you a sense of investment in national supercomputing. But the really cool thing about this model is it enables you to zoom in to 2.5 kilometers here. That would take 600 years to simulate 100 years on Australia's national supercomputer. Germany has quite a lot more computational capacity. But the model allows you to dynamically zoom in on areas that you're particularly interested in and look to see how things connect in a two-way nested way, which I think got a lot going for it relative to either statistical or dynamical downscaling. We're probably 10 years away from doing this in Australia. I think we have a reasonable expectation that if we can build a global 10-kilometer model, it will provide robust boundary conditions for downscaling if we can't go to the higher resolution. And for those who don't know, there is now the Access National Research Infrastructure Initiative based in Canberra at ANU, a multi-organizational collaboration. And if USQ wants to be involved in the next generation of national climate modeling, there is a process to engage with that, and USQ would be very welcome. Thank you. Do we have some questions?
Oh, thank you very much, Tanya and Andy, for two great presentations. And I'll now pass over to Kate and Louis to handle the questions. So please, if you do have any questions, put them into the Q&A function. Thanks very much, Louis and Kate.
Thanks, Scott. Andy, probably starting with you there, Mark I've lost the name. Mark Clarkson has put up some comments which you may like to respond to in private with him, but the main gist of the questions, if I interpret them properly, are in terms of the modelling, how much warming to date is due to anthropogenic gas, and what is the role of sunspots in climate predictions? So if you could quickly answer that, and then we have another question. Yeah.
I can see Mark's questions. I would need to take these offline because they're misinformed. Greenhouse gases explain more than 100% of the warming that's occurred to date. They're offset in part by aerosols. That's dealt with in detail in the IPCC report. The issues around Milankovitch is a red herring. These are I'm sorry, I've given up trying to deal with people who ask stupid questions that haven't read the report carefully. And I'm not dealing with skeptics anymore. It's a waste of my time.
Okay, thank you. So we might move on then to Shabaz's question. Shabaz says, many thanks, Tanya and Andy, very insightful presentation. My question is related to systematic or correlated risk, since they are vital for insurance industries and banks and other entities. So under climate change, are we expecting systematic or correlated risk to increase? Or do they become more sporadic and would then allow insurance or industries such as insurance to assist in managing that risk?
Not sure if that's for you or for me, Andy. Systematic risk, in the sense that it's understood in finance, is probably not what we're looking at here. That probably is more to do with transition risk. I have to say, it's not something I haven't read anything in this regard. But it is, I think it is foreseeable. But we would probably need to, I think any type of systematic risk requires some level of contagion. And for that to occur, you would need to have certain signals from a physical risk perspective that would cause that contagion to take hold. So I don't think we're there yet from a physical risk perspective, but from a transition risk perspective, I think we're getting close. Andy?
Yeah, I don't think I've got anything much to add to that. I think that's probably a fair summary.
Thank you very much. Thanks, Kate. We don't have any further questions in the Q&A, so I might chip in with one. And it's a little bit, you might want to, a little bit unfair because it goes beyond the scope of what you've been talking about. So my understanding of what you're talking about is that you're more concerned with formal disclosure and you've been dealing mostly with larger enterprises. So my question without notice is, have you had any thoughts about how smaller businesses can manage these sorts of risks? I appreciate that they don't have to do the formal disclosure, but just as a broader question, you're really interested in any thoughts that you might have had along those lines, because the next steps that Andy pointed out, they do seem like you do need to have a certain level of scope size in your business before you can tackle those in a serious way. Thanks.
I could make a little start on that, Scott. You're quite right that a multinational company can bring more resources to estimating its physical climate risk than a small company. But equally, a small company that works out of southern Queensland, for example, they actually have access to quite a lot of expertise in southern Queensland. They could pick up the phone and have a chat with somebody from University of Southern Queensland. And I'm not talking about a 2-year analysis of every wiggle within their business's sales, for instance. If I said to you, by the end of the day, Scott, I want you to see if you can see any correlation between El Nino, La Nina, and this Excel spreadsheet full of monthly sales figures, you could do that. And if there's nothing to be seen there, you perhaps advise that business quite differently than if you can see a clear waxing and waning of sales closely correlated with 2 or 3 of the key modes of variability. Now, that doesn't fully assess a business risk, but it does begin a narrative between that business and you lot on the sorts of areas they should be looking at and the sorts of risks that you see as plausible as emerging in the area that business functions. So if you're a little company working out of Armidale, you have a much less complex problem than if you're Rio. which makes it easier to form a relationship with meteorologists and climatologists who work in your area to move the debate forward. So I actually think if you're early in assessing your risk, it's good because you get that phone call into Scott when he's got nothing else to do because he's locked down, and he can do the analysis. The problem comes if you're slow and you're the 137th company to phone you. So there's actually value in getting moving as a business reasonably quickly and beginning to develop those relationships to see where your risks might lie.
Thanks, Andy. Tanya, did you want to add anything?
No, not really, other than just to sort of emphasize that with a smaller business that doesn't have the global footprint of someone such as a Rio Tinto, then the scale of the analysis that's required is obviously going to be lower. I think, so Andy's suggestions around the analysis of historical accounts is a very, very, very sensible one. It's not too complex. We have forensic accountants who do that sort of analysis quite regularly. And then it becomes more about forward-looking strategy, consideration of capital expenditure, and the timeframes around that, and where they would be located. So I think it's actually probably quite a much more straightforward process. Whereas if you've got global supply chains linked with global assets that you own and operate, I think you're looking at a very different level of analysis. Yeah.
Great. Thank you very much. I might hand back to Kate because we have two questions, one from Joe Owens from the Centre for Applied Climate Sciences and also from Tess Parker at UNSW. Thanks, Kate.
Thanks, Scott. Joe Owens asks, Andy, thanks for the warning for those of us working on small scales, particularly with pasture and crop modelling from experimental sites, paddock and farm scale. Could you please speak more to the point you made on not using data from single grid points?
Sure. The way that you take the fundamental equations and you solve them on a grid, the way you discretize those equations to solve them on a grid means that one should aggregate somewhere between 4 and 6 grid points to get robust forecasts or projections. You shouldn't use a single grid point. Of course, people use single grid points. But if you insist on using single grid points, it's a good idea to move your eye to the next surrounding grid points to see if you would get the same answer. In a global model or even a regional model, the co-location of the grid isn't geo-referenced in the way that you might think it would be if you look at a map. The coastlines are often not exactly where the coastlines would be in the real world. You don't usually have rivers. The mountains are smooth, lots of simplifications necessary. And that means that you have to be extremely careful in how you utilize information. That leads to a real mess for people working at the paddock scale. And my view is you're wise to be extremely cautious in using output from either downscaling or global models if you're working at the scale of an individual catchment. The way that we tend to recommend people do that, at least I do, is you take the changing statistics from the climate model or the downscale model, and you utilize the changing statistics to produce scenarios based upon historical data at the location that you're working, which is different. And you just have to produce multiple storylines or multiple scenarios. You need to do ensemble predictions and you need to use appropriate Bayesian statistics to tease out the right result. But those are things that you lot would be pretty familiar with.
Thanks, Andy. Another question from Tess Parker from Monash, I believe. Is there scope then for a somewhat standardised approach for business sectors or sizes in a particular region that is a template of sorts for that industry of that size in that region of what their exposure may be. So perhaps that's one for you, Tanya, or for Andy.
Yeah, it's probably more for Andy. Standardization in this area is very, very challenging in terms of at a region and for a particular sector. I think it's not either or. I think it's for a region and a particular sector. Andy?
Yeah, so I started to try and do that. I tried to produce sort of a template exactly as Tess asks, but because Tess works in the Centre of Excellence, I think this would be a really good role for her moving forward. I only teasing you, Tess. The problem comes that once you go past one or two steps, how you would do it becomes nuanced by the precise structure, nature, location of a business. So if you have two near identical businesses working in the same region, then you can do it. But something as simple as someone growing beef as distinct from someone producing milk, how you deal with climate change for those two, both agricultural sectors, both involving cattle, is quite different. And the risks are quite different. And so I don't know how to do it in a general way. Somebody cleverer than me might be able to do something in a generic way, but I couldn't do it. I got lost in the detail too quickly.
Yeah, I think when we're talking sectors, it's you have to go finer than, say, agriculture. So then we start looking more at something that's actually more bespoke in the way that Andy was talking through on the slides. But it has been done for particular sectors such as dairy, for example, in southeastern Australia.
Great. Thank you very much, Kate. I might chip in next. We're just about out of time. Thanks again, Andy and Tanya, for fantastic talks, really thought-provoking, very informative. And also thanks very much to Kate for looking after the Q&A with Louis, and also special thanks to Crystal for all the work she's done in helping us rejuvenate our seminar series. So this is the first in what will be many more seminars from prominent and fantastic researchers from around Australia and beyond. And our next speaker will be Neil Plummer, who formerly led climate services across the country for the Bureau of Meteorology, and he'll be talking about navigating business through the global climate and energy transition. And that'll be on Wednesday, the 1st of September, 10 a.m. to 11 a.m. So again, thanks very much to all of you, all of the people that participated in today's event. Bye for now.
Thank you. Bye.